Hello, and welcome to my presentation on the Send Hardest Problems My Way, Probabilistic Path Prioritization for Hybrid Fuzzing paper. Alright, let's get started. So we all know software vulnerability is considered one of the most serious threats to cyberspace right now. But the engineering reality is that modern code bases are massive. You cannot manually audit millions of lines of code. We need some form of automated vulnerability discovery. Traditionally, we rely on fuzzing, just throwing random inputs at a program to see what breaks. Fuzzing is incredibly fast and is proficient at exploring general branches. But as we all know from working on our own projects, just watching our fuzzers coverage graphs flatline, you know that they are just blind. If they hit a specific branch, like a strict magic number or characters or string check, they stall out since they are not able to guess that exact value. The response to this was concolic, also known as symbolic execution. Instead of just guessing, it looks into the code and the user's input to find the needed input to get through a branch. It translates the binary of the code into algebraic equations and uses a mathematical solver to generate that input. But there is a catch. Because concolic execution suffers from the path explosion problem, which makes it incredibly slow at large scales. But here's the thing. Fuzzing and concolic execution are complementary in nature. Combining them can potentially leverage their unique strengths as well as mitigate their weaknesses. This brings us to the concept of hybrid fuzzing, which has become increasingly popular in vulnerability discovery. The goal is simple. Let the extremely fast fuzzer do the heavy lifting and only run the slow concolic execution when the fuzzer hits a brick wall. Now the question is, how does that happen and how do the authors of this paper put that into practice? Let's just look at fuzzing, the first half of the equation. If you're building a fuzzer engine, you quickly realize that it's all based around a single metric, pure throughput. Fuzzing is the high-speed brute force method. It's incredibly proficient at exploring those general branches, essentially conditions that have many inputs, like testing if a value is greater or less than zero. As any random input, half of them will be able to pass that check. Since it can execute these thousands of tests in a second, it can brute force very efficiently, acting as a random sampling process across the program's state space, covering a huge amount of code essentially instantly. But here's the fatal flaw. Because it's completely random, a fuzzer is fundamentally blind to specific logic. As stated before, specific magic numbers or string comparisons, it'll hit a brick wall unable to progress. It's blind to the code, essentially just only knowing it failed the check but not knowing why. To get past that, we can't just put more hardware into this, hoping for more iterations of the fuzzer. We need a tool that can get past this. That brings us to concolic execution. If if the fuzzer is high-speed brute force, concolic execution is a heavyweight logical mathematical method, also known as dynamic symbolic execution. This is a tool we use to crack the specific branches that block the fuzzer. It works by, instead of blindly guessing numbers like the fuzzer, it executes and translates a raw compiled binary into an intermediate representation. By tracking the user input throughout the program and how it changes and where it goes, it's able to create a mathematical formula that eventually another mathematical engine will be able to solve. Yeah, here's the thing. That process is extremely heavy and takes a lot of time, many magnitudes of time more than creating random inputs like the fuzzer. And also suffers from the path explosion problem. which is part of why it's so expensive. Keeping track of all the mathematical constants and constraints is just very heavy. Just to give you a concrete number, in the DARPA dataset evaluated by the authors of the paper, it took a standard concolic executor an average of over 1,600 seconds just to process a single input, whereas a fuzzer could process that in a few milliseconds. So here's the dilemma. Fuzzing's incredibly fast, but has no math behind it to get past constraints. But concurrent execution can get past those constraints, but it's extremely slow. So we have to combine them. But the question is, how best do we know when to use one or the other? That's where hybrid fuzzing is. It's a combination of both fuzzing and concurrent execution. It takes the incredibly scalable, efficient fuzzing and then the very logical, heavyweight concurrent execution, leveraging their unique strengths while mitigating the weaknesses. In a proper hybrid scheme, the architecture relies on the idea that the fuzzer undertakes a vast majority of the path exploration throughout the program. Since due to its high throughput, it can do this much better than a concurrent execution would. This means the concurrent executor is essentially a specialized tool that only comes in when it's needed. It alleviates the path explosion problem since you're not running the concurrent execution on every single path. In theory, though, this sounds like the perfect solution, but here's the question that the paper really focuses on. Just how do you decide when to use each? Here's the first approach. A demand launch, as seen in previous research in a system like Driller. The general idea is to launch concurrent execution for when the fuzzer gets stuck. Essentially, if it fails to make any progress for any period of time, let's in this instance for 100 seconds, it will bring in the concurrent executor to take over, giving it all the branches that the fuzzer left off on. This undergoes a few key assumptions though. First, it assumes that a fuzzer that is in a non-stuck state, that concurrent execution is not needed. So essentially meaning the fuzzer is always able to make progress. Second, though, it means that if a fuzzer does get stuck after this 100 seconds, it assumes that it's unable to make any progress and only the help of the concurrent execution is able to help make progress. And it also assumes that the concurrent execution is able to find and solve the conditions that block the fuzzer. Another approach that was explored was also the optimal switch method employed by research done with MDPC. Here's the idea. Instead of always launching the concurrent execution, you estimate the cost of both of running either one on any given branch, and then choose whichever one has the lowest cost. So the cost of fuzzing they use is based off either the coverage statistics for fuzzing, and then based on the constraint complexities of concurrent execution. This assumes that the estimations of both are accurate and fast, and that the decision making between which to use is lightweight. Now let's look at the findings of those papers. So we established that demand launch assumes two things. Making progress means you don't need help, and that getting stuck means you do. The authors of this paper put this to the test by running Driller against 118 curated binaries for 12 hours. They gathered data that proved these assumptions wrong. First, the stuck state is a horrible indicator for needing concurrent execution. Looking into the data, the fuzzer only got stuck on 49 out of the 118 programs because the fuzzer was still finding new shallow code in the other 77 binaries. The driller thought everything was fine and left the concurrent executor asleep. But those 77 binaries still had deep specific branches that blocked the fuzzer from finding vulnerabilities. It was just finding more in very shallow areas of code that didn't need it. Because just just because the fuzzer is making progress doesn't mean it isn't missing that crucial code. Furthermore, when it did get stuck, 85% of the times it did, it only lasted below 100 seconds, meaning it wasn't often truly stuck. Secondly, the man launch has no concept of prioritization. It cannot recognize a specific path that caused the robot. Like stated before, when the fuzzer gets stuck, it just dumps every single input that it had to the concurrent executor and tries to have it go through each one. This takes an exorbitant amount of time, taking an average of over 1,600 seconds just to process a single input. And since the fuzzer generates thousands of seeds, this simply overwhelms the concurrent executor and its math engine, being able to only process 7% of all the seeds before the 12-hour timer ran out. Moreover, only 51 inputs of the concurrent execution were imported by the fuzzer after the 1,700 runs of the concurrent execution, which indicates a very low quality of inputs generated by that concurrent execution. So the result? The concurrent engine only managed to successfully help the fuzzer on 13 out of 118 programs. The reason it being is just simply too blind to the code and gets overwhelmed immediately. Going on, so now we know the main launch is too blind, but what if we take a manager approach to this, managing every single decision? This is what optimal switch strategy does. MDPC is decision making is heavyweight. It tries to mathematically calculate the cost of exploring a path before it even takes that step. On paper, this sounds like a great idea in order to best allocate resources. In practice, though, it results in a very fundamental paradox. To calculate how expensive it will be for the concurrent executor to solve a path, it has to do steps it would have taken if it was run normally, like translating the binary into an intermediate representation and collecting the path constraints. But as we established, that exact process is what makes concurrent execution so slow. The MDPC forces the system to pay this massive performance tax, like just on every single seed, not just the ones that concurrent execution runs on. The overhead of doing this before every single execution completely diminishes any gain that it could have gained. The paper notes specifically, throughput plummeted from 417 executions per second just down to 2.6 executions per second, really showcasing how slow this made it. Because the decision engine completely hindered the fuzzer speed, MDPC actually performed worse if you just let the fuzzer run blindly by itself. In the data, Pure Fuzzing found bugs in 67 binaries, with MDPC only finding them in 29. So here's the catch. So Driller waits too long, and MDPC thinks too hard. We need a system that can actually prioritize paths without slowing the fuzzer down. So this is what the authors of this paper did by creating DigFuzz. DigFuzz and this core principle of discriminative dispatch. This avoids the traps that the previous methods fell into. The authors established two strict design principles. First off, let the fuzzer do what it does best, taking over the brute force uh, option with high throughput that explores the vast majority of paths. Secondly, treat the concurrent executor as a highly scarce resource, only allowing it to solve what the what the what problems would take the absolute hardest and like take the most resources. Do not let the concurrent executor waste time on and resources on a path that the fuzzer could eventually guess. But but how do we establish that? And how do these rules introduce a massive engineering challenge? Why? How do you know if a hard problem is hard for a fuzzer, and how do you know which one is the hardest? We also need to ensure that any extra analysis used to quantify path difficulty has to be incredibly lightweight. If the analysis is too heavy, you'll fall back into the same trap the MDPC did and destroy the fuzzer's throughput. So we know we cannot use heavy symbolic math like that using concurrent executors to do the cost analysis because it's simply too slow. We need a faster way to score them. And that brings us to the statistical model that makes DigFuzz work. How do we analyze a path difficulty without tanking performance? DigFuzz's solution is simple yet ingenious. We don't analyze the code any more than it needs to be. We analyze the statistics that the pure fuzzer gathers already. Most modern fuzzers already maintain a lightweight shared bit memory bitmap to track how many times it hits certain blocks, which tracks overall code coverage. DigFuzz just utilizes this already known data and treats the fuzzer's high-speed random guessing as a massive Monte Carlo simulation. Essentially, it's just taking this massive input and making and applying it to the probability of each path. Specifically, score any given branch. It looks at the hit counts of any of each branch, and if so for instance, if a fuzzer passes a parent block 10,000 times and takes 2,000 of those 10,000 times, the probability is the simple 20%. So the probability of any block is based so purely on its parent and sibling. This is simple and uses already known existing data. Now, there's the edge case that if a branch has 0 hits, the authors of this paper use a statistical concept used the rule of 3. Essentially, if the fuzzer hits the parent block n times, but never hits this target branch, the estimated probability of that missed branch becomes 3 over n. As the fuzzer runs and n gets larger, the probability of that missed branch mathematically shrinks. So now that every branch has a possible score, scoring an entire path, the DigFuzz models the execution trace as a Markov chain with each event relying and influence the next. Because each branch decision relies on the previous state, finding the probability of an entire execution path is straightforward. It's simply just multiplying all those probabilities together. By using this math, DigFuzz dynamically builds a statistically weighted execution tree in the background using only the data that the fuzzer already gathers. It scans the tree, finds the path with the absolute lowest mathematical probability, and sends only that path to the concurrent executor. No heavy symbolic constraints needed. Now let's look at how this actually did in reality. The authors tested DigFuzz against the same 118 complex binaries from the DARPA dataset. But in addition, they tested against 4 real-world programs from a level M dataset, pinning it directly against standard fuzzers and the older hybrid models we just discussed. Additionally, it introduced a random model, which does what DigFuzz does, except it has no decision making on when to implement the concurrent execution, being completely random. So providing a baseline on how this decision making actually makes an impact over just random guessing. So the results prove that the statistical math works. Digfuzz achieved the highest overall code coverage, beating every other baseline. Data show that because the concurrent executor was only fed the hardest paths, it never got overwhelmed, and the inputs it generated were very valuable, directly resulting in more discovered crashes. It didn't win by throwing more hardware and creating more throughput. Dick won by having a smarter algorithm and being able to achieve similar results with half the running time and much less hardware compared to Euler. To bring everything together, I just want to reiterate just how massive an achievement this hybrid fuzzing was for vulnerability discovery. We took a fundamentally blind technique, throwing data at a wall and see what breaks, and successfully combined it with the heavy, precise mathematics of symbolic execution. But as we saw today, just simply putting these together in any way isn't enough. The real catalyst for success was the Dick Fuzz's discriminative dispatch strategy. By utilizing a Monte Carlo probabilistic model, they figured out how to mathematically quantify path difficulty using the data the fuzzer was already collecting. They solved the ultimate engineering bottleneck, maximizing the power of concurrent execution without sacrificing the throughput of the fuzzer. Now this brings us to now. As we are all graduating and moving into the industry, or even just going back and working on our own projects tonight, it leaves us with a critical lesson. It isn't always about having the fastest or most complex code base. It's about the orchestration of the parts it makes up. The question I want to leave you with, as future computer science professionals, how can we apply this exact philosophy using lightweight heuristics